welcome to the class Advanced Reaction Engineering. So, today we will discuss about bioreactors. So, already you have started. So, basics about the bioreactors, cell growth and different stages for a cell growth in a bioreactor. So, that we have discussed, also the Monod equations, that also we have discussed. So, today we will discuss about the stoichiometry, yield coefficients, rate of substrate consumptions, product formations and secondary nutrients that is required for a bioreaction. So, that basically we will discuss. So, stoichiometry, yield coefficients for the cells, substrate and products, cell maintenance, substrate utilizations, product formations, maybe growth phase and stationary phases, the product formations and the secondary nutrient that is required. So, that also we will discuss for a bioreactors or bioreactor systems. So, already we have discussed the means bioreactions, means for a bioreactions we need a cell, new cells and then substrate that we required, that we have to put inside of a reactor, that is called bioreactor. So, then new cell formations or cell growth would be there, at the same time product formations would be there. So, the stoichiometry, if you want to get any or talk about any reactions, so reaction stoichiometry is very important. So, means let us say for any general reactions we usually express A plus B going to C plus D. So, the stoichiometry for this particularly for bioreactions, the stoichiometry for the cell growth is very complex and varies with the microorganism, nutrient systems and the environmental conditions that we use for a bioreaction systems, basically pH, temperature, redox potentials. So, stoichiometry means evaluations or find out for a bioreactor systems is very complex. So, it is very complex when more than one nutrients contributes to the cell growth. So, that may possibility is there, means once we conduct any bioreactions in a bioreactors, we are supplying the nutrients for the cell growth. So, maybe one particular nutrient that is used for the cell growth, maybe other nutrient that is not used at the times, maybe some other stages, that second nutrients or secondary nutrients maybe has some influence to form the product formations. So, different stages we have discussed. So, that we have to discuss, means we will discuss means how to find out stoichiometry for a particular bioreactions. Next is the means, if once we know that when we are using a substrate for a bioreactions, the cells we are using, at the same time substrate we are using, as a result we are getting a new cell forms, that is forms in the bioreactions, at the same time some product that is generated that we are getting. So, means in the reactions you can see this is the reactions. So, in the left hand side we are using cells and substrate and right hand side we are getting more cells and product. So, here the concentrations means individual component, means cell, product, substrate, how we can express with each other, means if we have a fixed desired product formations, then how much quantity of substrate you have to use, how much quantity of the cells are required, or to get a particular product how much means we can correlate substrate with product, we can correlate substrate with new cell formations, okay, and with the cells with the products, that way we can correlate, means per unit product formation how much substrate is required. So, that basically yield or expressed in terms of capital Y for the cells as well as substrate. So, YCS we are expressing, that is the yield coefficient, it is expressed in terms of Y. CS, C is the mass of the new cells formed per mass of the substrate that is being consumed during the reactions. So, I said whenever bioreactions or reactions we are conducting, we are supplying the substrate, as a result we are getting new cells that is formed. So, at the end of the reactions, if we measure the quantity that new cell forms and the mass substrate that we have used for the systems. So, we can write this way. Okay. So, means minus delta Cc by delta Cs. So, here the new cell formations, initially the amount of the cells we have taken, and at the end of the reactions the total concentration of the cells that we have been formed. So, if we subtract that, then the difference would be the new cell formed during reactions are delta Cs, that is the substrate initially you have taken, and at the end of the reaction the concentration of the substrate if you know. So, then the difference would be delta Cs. So, by that way delta Cs is the means if we know, then we can yield of the means mass of the new cell formed per unit mass of the substrate that is consumed, or else we can write this equation 1 in terms of this way also, YCS equals to 1 upon 1 by YSC means substrate consumed per unit cell, okay, new cell formations, the how much of substrate is required. So, that way also we can write. Okay. So, here's Monod equations that we have written here. Here you can see Rp, that is the rate of formations of the products, that we can write Ypc into Rg. What is the Rg? Rate of formation of the cell. Okay. So, Rg equal to rate of formation of the cells, Rg we can express in terms of dCc by dt. So, Rg equal to dCc by dt, that is the rate of formation of the cells that directly proportional to the mu into Cc, specific growth rate and cell concentrations. Okay. So, here's in a bioreactions I said in the left hand side substrate and cell is there, in the right hand side product and new cell formation is there. So, how much quantity of the product formations means when a cell reactions is there, substrate gradually consumed and new cell formations, Rg is the new cell formations is there, Rg rate of formation of the cells. So, with that cells in the right hand side you can see there is the product is there, that may be ethanol for a particular reactions or maybe some other compounds or components formations is there that are useful. So, if we want to know the rate of formation of that particular product, so then we have to express in terms of Rp, Rp equals to Yp by C into Rg. So, cell growth from the Monod equations we know. So, Rg we know from here, from these equations. Okay. So, this we can substitute here, then Rg equals to mu max Cs Cc by 1 plus Ks plus Cs. So, Monod equation that we have discussed. So, that we know rate of formation of cells, and Yp if we know, that is the yield coefficient product Ypc, Pc is the product formations per unit cell that we have used. Okay. So, then Rp equals to rate of product formations equals to Ypc into Rg, Ypc equals to, and Rg that we can substitute here, Rg equals to mu into Cc, we can substitute here. So, then Ypc is there and mu we can substitute, mu equals to specific growth rate, that we can substitute here, then these equations we can get. Okay. So, Rp equals to rate of formations of product equals to yield of the product per unit cell, and this is the rate of this Rg, basically rate of cell growth rate. Okay. So, equation 2 we can use for the formations of the product formations during bioreactions inside of the bioreactors. So, for that we need to know Ypc, Ypc we have to know. Okay. So, here's Ypc into mu, that we can say that specific rate of product formations, Ypc into mu, that you can say Qp, that is the mass of product formed per unit volume per unit time. So, here's Rp we can find out by using these equations. Okay. So, here's Ypc, what is Upc? Ypc I said mass of the product form per mass of the new cell form, or delta Cp by delta Cc. Delta Cp, that is the changes of the product from initially it was 0 and at a particular specified time t, that would be some concentration of the product, that concentration that particular product formation is that we know, that difference would be this, and delta Cc, that is the cells initially we have taken very small number of cells and after t time a number of cell formations would be there, that difference would be this. So, Ypc easily we can find out, okay, that we can substitute here, and then rate of product formations easily we can find out. Okay. So, rate of product formations also we can express in terms of substrate consumptions. Okay. So, rate of product formations here we can express in this way. Okay. So, the rate of product formations also we can express Rp equals to Yps minus Rs. What is RS? Minus RS, RS is the rate of substrate consumptions, okay, substrate disappearance during the reactions, minus RS, minus sign is for disappearance or gradually decreasing in concentrations, and S for S indicates substrate, means for any cell reactions we have to use cell plus substrate, that would be converted into product and new cells. So, rate of substrate disappearance if we are able to know, and YPS if we know, YPS that is the yield of the product per unit cell, YPS. YPS we can express similarly this, YPS is the yield of mass of the product that is formed per concentration of the substrate, YPS. So, if we know YPS for these reactions and rate of disappearance of the substrate, then if we multiply that way also we can express rate of product formations by on the basis of the substrate consumptions. Okay. So, here's this is the reactions, most of the cases we said or we will write for the bioreactions when we are conducting in a bioreactor. So, yield of the substrate, yield of the cells, YCS, here we have expressed YCS, Y usually we express in terms for the expression of the yield. So, CS that is the mass of the cells that is formed, mass of the substrate that is consumed. So, cells formations by substrate consumptions. Okay. So, it is in the right hand side you can see minus delta Cc by delta Cs, minus delta Cc here, this is the delta Cc and delta Cs is this. These terms here you can see delta Cs, you can easily you can see initially substrate concentration was high and then substrate after reaction Cs that would be a decrease, means substrate concentration as the progress of the reaction that will gradually decrease. Therefore, the terms delta Cs terms would be positive and substrate cell concentrations that is gradually increasing, Cs0 minus Cc that is increasing. So, Cc that concentrations would be higher than Cc naught, okay. Cc concentrations would be greater than Cc naught, okay. Since new cell formations is there, therefore, this part would be negative, okay. So, therefore, this minus sign is coming in this case, okay. So, YCS that mass of the new cell forms per unit mass of the substrate consumption yields that we can express in terms of this. Similarly, yield of the product forms that is per mass of the new cell formed, means at the right hand side new cell forms and product formations. With respect to the yield we can express Yp by C. Okay. So, mass of the product formations is there, delta Cp that is the this, okay, product formation also gradually increase. So, delta Cp would be negative and delta Cc that is also negatives, both negative and negatives would be subtract, minus delta Cp minus delta Cc. This way we can eliminate this part. So, then it would be Ypc that would be mass of the product form per unit mass of the new cell forms, we can write this way. Okay. So, similarly, the stoichiometry yield coefficient that relates with the amount of the product form per mass of the substrate consumed. Okay. So, Yps we can write minus delta Cp by delta Cs. Okay. So, this way also we can write. Okay. So, yield of the cell, new cell per unit substrate, yield of the product per unit new cell forms, yield of the product form per unit substrate consumptions, that way we can write. Okay. So, whenever we do the any bioreactions in a bioreactor, so initial concentrations of individual component cell substrate is known, more cell final when the reactions is stopped, then the cell concentration known, product that our target product or known product that is formed, the product concentration is also known. So, everything is known, only then based on that the yield everything this way or this way you can express the yield coefficient, we can easily find out, then one component concentration to another component easily we can interconvert. Okay. Next is the cell maintenance. Whenever we are using a bioreactor for a bioreactions, then cell maintenance that is very crucial part. In the stationary phase there is no cell growth, means once exponential growth rate is there, at that stage the cells will consume the substrate and number of cells gradually will increase. means after that times when there is no further new cell formation is there. So, at that stage cell only consume the substrate that is present inside of the reactors. So, therefore, whenever we are doing these reactions or we are doing talking about this stoichiometry. So, new cell formation is there, reaction stops. So, then to survive or this life of these particular cells we need substrate to maintain. So, that is called actually cell maintenance, not only for the productions of the new cells, to maintain the cells in cells daily activities. So, we need substrate also. So, then therefore, the substrate is used for the new cell productions as well as maintenance of the cell daily activities. So, both the way the means substrate that we are using for the cell culture that are used. So, that usually expressed in terms of the M, that is the maintenance or cell maintenance, that the amount of the substrate that is being used, or mass of the substrate consumed for maintenance, mass of the cells per unit times. So, M or the amount of the substrate that would be consumed during the cell maintenance times, that depends on the number of cells present inside of the bioreactors. Okay. So, therefore, M we can express mass of the substrate that is consumed for maintenance per unit mass of the cells per unit time. Okay. So, or else here M is the maintenance utilization term, M is called. So, then the rate of the substrate consumptions for maintenance, means for the cell maintenance, means the rate if you want to calculate, this is for M we have expressed this way. And now, if we want to calculate the rate of substrate consumption during the cell maintenance, that we can the rate we can express RSM. RSM is the substrate. Okay. So, the cell maintenance, the amount of the substrate is used. Okay. Substrate consumption, that is M into Cc, the number of cells present in that reactor, that is very important. So, here if this is and total number of cells if we multiplied, then mass of the substrate consumed per unit time, that is the rate we are expressing RSM. So, if we want to know that, so then these equations or equation 5 we have to use, and if we know M and concentration of the cells, so then easily rate of substrate consumptions at cell maintenance times, that we can easily find out. Okay. So, if we neglecting, sometimes we can neglect the cell maintenance. So, then the concentrations of the cells formed to the amount of the substrate consumed we can express by these equations also, means YCS, that is the yield of the cells per unit substrate consumptions, and this is actually we have expressed this YCS equals to mass of the new cells forms by the mass of the substrate that is consumed for the reaction. So, then this YCC, that is the cell concentrations, we can or if we neglect the cell maintenance part, then Cc we can write YCS into CS0 minus Cs. These equations 6 is also useful for the batch reactor or as well as continuous reactor also we can use. Okay. So, now substrate, suppose if we are using the substrate for the cell culture in a bioreactor. So, inside of the reactors we are supplying the substrate, and at the same time we are supplying the cells also. In the when new cells are present, the substrate will be consumed. Means substrate may be different type of substrates are present. So, if we are able to sort out the substrate, okay, it is not possible, but if we are able to sort out the substrate that is consumed in the presence of the cells to form new cells from the substrate that is being consumed to form the new products. So, then the cell equations we can write S equals to S, and this is the new cells, this way we can express. Okay. So, yield, this is the yield coefficients we are expressing, and right hand side yield coefficient for the product, yield coefficient for the substrate multiplied with the substrate cell concentration multiplied with the product concentrations. So, then substrate we can express or yield coefficient we can write this way, mass of the YCS. What is YCS? Y prime CS, that is the mass of the substrate that is consumed to form new cells to the mass of the new cell form. Okay. And YPS, y prime Ps, that is the mass of the substrate consumed to form product per mass of the product formed. Okay. So, this way also we can express. So, means substrate as well as product that forms and the new cell formations is there. This way also we can express. And next is the substrate utilizations. Substrate utilization. So, means I said that when cell reactions is there. So, in the cell reactions the substrate that we are supplying at the beginning of the reactions for the bioreactions in the inside of a bioreactor, the substrate that present inside of the reactors, that is used for the cell formations, product formation as well as cell maintenance, means the substrate that we are supplying for the cell reactions, that is used three way: cell formations and product formations as well as cell maintenance, the substrate that is being used. Okay. So, then the rate of the nutrient, that is the substrate we are supplying for the cell growth, rate of substrate means I said these are the three way it is consuming. So, then net rate of the substrate consumptions, here this substrate is consumed by these three way. Okay. So, for more cell formations, product formations and as well as cell maintenance. So, then minus Rs, that is the rate of substrate consumptions inside of the reactors, we can express yield rate of the cell, rate of the consumption by the cells, rate of the consumption to form product, rate of the consumption of the for maintenance. Okay. The substrate that are used in this three way. So, that means then net rate of the substrate consumptions we can write minus R is equals to y prime S by C into R g, that is the rate of cell formations. If we are know, means that at the beginning we have written R g equals to rate of cell formations, this way mu into C c, this way we have written the rate of cell formations. So, if we know the rate of cell formations rate and y prime S c, if we are know means yield, means substrate formations per unit cell consumptions or per unit cell formation, the amount of the substrate consumed. So, then if we multiplied with this rate, so then the amount or rate of the consumption of the substrate for the cell formations, that we can write this way, and rate of the consumptions for the product formations. If we know the yield coefficient for the substrates that are used for the product per unit product formations, then rate of product formation, that equations we have also discussed. These equations, rate of product formations for these equations and these equations or we have used. This is rate of cell formations, this is the rate of product formations, these are the equations we know, and corresponding yield also we know. So, then y prime S p yield for the substrate per unit cells, yields of substrate per unit product, and rate of product formations if you know, rate of cells formations or cell growth rate if you know, if we multiply with this of this, and for cell maintenance also we said that m into C c, that we have discussed the substrate consumption, substrate three different way consumed. So, then the rate of substrate consumptions for cell maintenance equals to m into C c. So, three component if we sum up, then total rate of substrate consumptions during the bioreactions that we can find out. So, then what are the component we need? AMCC, y prime S by P into Rp, y prime S by C into Rg. So, these are the components if we are able to know, then rate of substrate consumptions, total substrate consumptions for the reactions we can find out. Okay. So, now the case 1 and case 2 we will discuss here. These are the things we have discussed in our previous class also, means the how with the time progress of the times, the changes of the cell growth, means cell concentrations inside of the bioreactor. This is the lag phase, this is the growth phase, and this is the stationary phase, and this is the death phase, that already have discussed. So, means use of the substrate. So, all substrate that are consumed each lumped into the stoichiometric coefficient or YSC, and the rate of the substrate disappearance, that we can express this way, rate of the substrate disappearance. So, here that is the growth associate for the product formations. Okay. So, growth associated with the product formations at this particular or exponential growth is there. So, if we express the rate of the substrate disappearance minus R s, that is equals to yield coefficient Y s c into R g and M c c, means and corresponding rate of product formations is R p equals to R g into Y p c, Y by p c, that way we can write. Okay. So, rate of product formations we can write this way, and rate of substrate consumptions we can write this way. Okay. Rate of substrate consumptions by using equations this, and rate of product formations we can write this, means here the growth rate. See, here's the consumptions of substrate that are here's mainly consumes here for the growth of the cell growth. At the same times product formations may be either here or here product formations. So, here cell formations is there or new cell growth is there or new cell formation is there. At the same times here product formation is there or not, that is very difficult to distinguish, but here also may possibility is there, cell product formations possibility is there. Most of the cases product formations usually stationary phases are there, so their product formations are there. So, here means the rate of consumption of substrate that basically is used for the cell maintenance. Okay. But at this particular point, so this part means cell growth as well as cell means maintenance. Okay. So, that substrate that are being consumed at this particular positions. Okay. And in normal case 2 that we will discuss, that is the secondary or different nutrients that are also being consumed for the product formations. In that at this particular phase is the non growth associated product formations in the stationary phase. So, here no growth means no non growth associated product formations, it means at this particular point product formations is there, but no new cell formations is there. Therefore, the substrate consumptions here only we can say that is for the cell maintenance and product formations is there. So, at this case see here there is no cell growth during this stationary phase, and the equations 8 cannot be used to account for the substrate consumptions. Equations 8 that we have used that cannot be used, since here means product formations is there, but for the substrate consumptions we cannot used, and it also cannot be used to for the rate of the product formations related to the growth rate, since most of the antibiotics, that is the penicillins that are produced in the stationary phases. At this particular phase most of the product formations is there. In this phase the nutrients requires to growth becomes virtually exhausted, and the different nutrients may be, that is the secondary nutrient that may be used for the cell maintenance and the desired product formation. So, at this particular stage, so there is non growth associated product formations is there in this particular phase. So, here the normal nutrients that we are using for the cell growth in this stage, not only the normal nutrients, there is some another nutrient or different nutrient or second nutrient that may be used at this particular stage for the product formations. So, that is very important. Okay. So, therefore, at this particular stage non growth associated phase, or when there is a secondary nutrient that is being consumed for the product formations, the rate law monotype of similar type of rate law we can means for the cell growth associated we can used, or we have used this type of rate law for the product formations. So, in this case, in case of stationary phases, non growth associated phases. So, in that case the rate of formations of product we can write this way, means this is also monod equations, but we are expressing in different way. R p equals to K p into C S n, that is the concentration of the secondary nutrient that is present, and concentration of the cells by K S n plus C S n. K S n is the monod constant and C S n is the concentration of the secondary nutrient. So, if you know the secondary nutrient concentration, cell concentrations, so this equation monod equations we can use to find out rate of product formations at this particular stage, non growth associated product formation in the stationary phase we can find out. Okay. So, here Sn is the monod constant, Cc is the cell constant concentration, and Csn is the concentration of the secondary nutrient, and Kp is the specific rate constant with respect to the product. Okay. So, similar like these equations for this growth phase, this equation was used, and for these stationary phases, if there is a product formation is there and the product formation is there due to the consumption of the secondary nutrients, then in that case we can use these monod equations to find out rate of product formations in if we know the concentration of the secondary nutrients as well as cell concentrations. So, these equations we can use and we can find out rate of product formations. Okay. So, rate of product formations we have expressed these equations, okay. And the secondary nutrient that is consumed in the stationary phases, that we can write this way, that we have discussed. Okay. So, in the second stationary phases, so here's rate of consumption of secondary nutrients, not normal nutrient, that is secondary stationary phase, there is a product formation is there by consumption of the secondary nutrients. In that case, the consumption of the secondary nutrients or rate of disappearance of secondary nutrients, we can express this way for the cell maintenance as well as rate of product formations. With that we have to multiply it the yield coefficient for secondary nutrient consumptions for the product formations. Okay. So, this if we are able to know, and rate we have to substitute here. So, then rate of secondary nutrient consumptions, that we can write this way, or we can express after substituting this equation 8, 11 we can write. Okay. Rate of desired product is produced when there is no cell growth, and it is always best to relate the product concentration to the change in the secondary nutrient concentrations. Okay. So, here's the product formations, that is we have expressed in the stationary phases, that is in terms of secondary nutrient consumptions, rate of secondary nutrient consumptions, and see here the concentration of the secondary nutrient, this is the concentration of the cells, this is the concentration of secondary nutrients, and this is the yield coefficient for secondary nutrient per unit product formations. Okay. And these are the constant, monod constant, or Kp also, that is also constant, and Cc is the cell concentration that we know, and M is the, that is the for cell maintenance, that is the constant. So, in these equations secondary nutrients concentration, cell concentration if you are able to know, and other component if known. So, then rate of disappearance or consumption of the secondary nutrients for the stationary phases cell means product formations, we easily can express or we can easily find out. Okay. Or else for the batch reactors also or batch system, the concentration of the product forms after a times in a stationary phase, that we can relate with the concentrations of the secondary nutrients. Okay. So, if we are able to means neglect the cell maintenance concentration, here cell maintenance also we have include here. So, if we are able to ignore or neglect that part for the cell maintenance, the amount of the nutrient consumption. So, then rate of or concentration of the product formations we can write in terms of yield coefficient, product formations per units substrate consumption, and secondary nutrient, the changes of the concentration of the secondary nutrient initially and after T times, the consumption should be, if you are able to find out for that bioreactor analysis, means when bioreactions should be there inside of the reactors, you know the what is the secondary nutrient and its concentration at the beginnings and at the ends. So, that concentrations if you are able to know, and yield coefficients product per unit substrate concentrations if you are able to know, then concentration of the product easily find out by neglecting the cell maintenance terms. So, equation 12 we have to use to find out the product concentrations. Thank you. So, today is up to this. So, in this study what are the things we have studied. So, various yield coefficients, this is the stoichiometry for the cell reactions, and this is the yield coefficient for component means substrate, cell or products. So, we can express by considering two different components, either way you can express, means here C by S means concentration of the cell or means mass of the new cell formed per unit substrate consumed, or else this way also we can write Monod equations we have discussed. Okay. And for yield of product formations, rate of product formations, that we can write this way also, means here yield coefficient is required. Okay. So, means rate of cell formations if we are able to know, then using that RG component, and yield coefficient we know, yield coefficient means product per unit cell, yield coefficients if you are able to know, then if we multiply it with the rate of cell formations, then that will give rate of product formations. Okay. That we have known. Okay. And YPC how to find out? So, YPC, Y by PC product rate of mass of product formations per unit new cell forms. So, by this way you can find out, and all the components if you are able to know. So, then rate of product formations we can find out. So, rate of product formations, rate of cell formations. Okay. So, these are the Monod equations we can use. Okay. Or these are the way also, means we can express, means rate of product formations in terms of substrate consumptions also we can use. So, once we means know the rate of substrate consumptions and yield coefficient for product and substrate, if we are able to know, then rate of the product formations we can find out using these equations, and some other way also yield coefficients we can express. These are the way, and each terms easily we can find out if you know from this stoichiometry individual component concentrations before and after the reactions inside of the bioreactor. That way we can express. And cell maintenance terms also we have discussed, means rate of secondary substrate cell maintenance, the rate of substrate consumptions. So, that also we can means the rate equation RSM, that we can express M into Cc, means if you know the cell concentration inside of the reactors in the stationary phase. So, then how much concentration of the substrate that are being used to maintain the cell, for that is called cell maintenance. So, rate of consumptions of the that we can substrate consumption, that we can find out using we can calculate by using RSM equals to M into Cc. Okay. M easily we can find out by using this. Okay. And cell concentration from the experiment we have to find out, and then RSM you can rate of substrate consumptions for the cell maintenance we can easily find out in the stationary phases. Okay. So, these equations we discussed, and this is the substrate and yield concentrations, product concentrations we can express in terms of yield coefficient and corresponding substrate consumptions. That way also we can express. And total substrate utilizations, that also we have discussed, means the substrate that is being used for the cell reactions. So, what are the different way that are being consumed, means for the cell productions, product formations and cell maintenance. These are the three way the substrate that we are using for the bioreactions, for the reactions. So, that are being consumed. So, how they are, means net rate of substrate consumptions if you want to calculate. So, then individual three components you have to add up sum of, then only the total substrate consumptions we can find out. If either total substrate consumptions is known, rate of substrate consumption for the new cell formations if you know, and rate of consumptions of the substrate for the product formations we know, then this total rate of consumption of the substrate for the cell maintenance, that easily we can find out. Okay. And if we ignore that cell growth associated means product formation at this phase. So, this way also substrate consumptions we can find out by using equation 8, and stationary phase the substrate consumptions we can use this way also, means secondary nutrient consumptions. So, how they are consuming, rate of net rate of the secondary nutrient consumptions during the stationary phases, that we can write this way. Okay. Okay, thank you. So, today is up to this.